All right, last lecture. Hope you enjoyed the semester. I actually realized that we got through, which is page 800 in the book. So congratulations. But we skipped a lot of stuff. So anyway, I decided let's talk about entanglement distillation. We can talk about the main ideas there. There's a chapter dedicated to entanglement distillation, and then if we would have had more time, we would have built up to the quantum computation based on entanglement distillation. But we'll just do this, and you'll have a sense of it. And it's another situation where it's kind of impossible to go through the whole gory proof, so I'm going to just summarize it. I think we've talked about it a little bit already. I made some references to entanglement distillation. So that this is possible, or that this is interesting, was first, this was John Smollen's PhD thesis in 1996. Before some of you were born, I don't know. Anyway, why is it important? Well, we want to know if we have some state, how much resourcefulness can we extract from it? Okay. And by resourcefulness here, the resource, the sort of golden unit of a resource is a maximally entangled state. Why is that? Well, for one, it's useful for basic tasks like teleportation, superdense coding, and quantum key distribution. And more recently, we've seen entanglement-assisted communication as an extension of superdense coding. Okay. So what is the setting? Again, we're going to do the one-shot setting. So we imagine we have a single copy of a resource state, rho AB. And Alice has one share, Bob has another share. So, okay. And then they're allowed to do any local operations in classical communication channel. So we talked about what is LOCC in the context of entanglement measures. And we'll again see today that entanglement measures are relevant for getting upper bounds on distillable entanglement. Okay, so then outcome systems A hat, B hat. Okay, and an entanglement distillation protocol is defined by a channel, an LOCC channel, and parameter D, which is the dimension of these final systems. Okay? And the way we quantify error is just using fidelity. Okay, so the error probability is just this: 1 minus the fidelity of the actual state at the end with the maximum entangled state of dimension D. That's the target. Okay. And we can rewrite this so that, remember the interpretation of fidelity, when one state is pure and the other is not, it's the probability that the actual state of the protocol, so just this fidelity, is the probability that the actual state at the end of the protocol would pass a test for being the maximum entangled state. And then 1 minus that is the probability it will fail the entanglement test. So we can rewrite this like this. And I think throughout, we call this final state omega. I would just do that. So it's the probability that the final state fails entanglement. Okay. And then the key quantity, throughout we would define like a one-shot capacity or a one-shot data compression limit, right, for data compression. Now it's going to be a quantity called distillable entanglement. What we want to do is extract as large a maximally entangled state as possible so that we can do as many teleportations as we want, or as many teleportations as possible, subject to the constraint that the error probability is less than epsilon. So very similar conceptually to what we've already been talking about. So this quantity is called one-shot distillable entanglement. Okay, how is it defined? Supremum over all dimensions and LOCC channels. The number of EBITs, right? So log 2 of D is the number of EBITs that you can extract. That's like the number of qubit teleportations you could do. Subject to the error probability constraint. Okay, and like we've been doing the whole time, we're interested in bounds, right? A lot of quantum Shannon theory, in light of not having solutions, the next best thing is to get a bound, right? So that's why we're so interested in bounds. Okay, so first, let's consider an upper bound. And it's going to be based on something called the Raines relative entropy, after someone named Eric Raines. Okay. So previously, when we tried to get upper bounds, we've done it now for classical communication, entanglement-assisted classical communication. We did it also for private classical communication. No, we did not. We did not. We did the lower bound. But a key concept is in all of these upper bounds to compare the actual state versus one that's useless for the task. Okay, so which states are useless for entanglement distillation, or which states are useless for teleportation? Severable states, exactly. And we can quantify that precisely. So, the first question you should think when trying to get any upper bound is which states are useless for this test. Okay, and we're going to see Connor's going to give a presentation on resource theories, right? And maybe somebody else. Yeah, and this same concept is there when you're trying to get upper bounds in general resource theories. You have to think about which states are not resourceful for the task at hand. Okay, so which states are useless? Sorry, I said separable states. It's kind of intuitive. They have no entanglement, right? But we can make this quite quantitative. So we can show that if we do the entanglement test, so suppose right here we do this entanglement test for a separable state. Okay, suppose that omega is separable. So let's do phi d AB, we'll lose the hats for now. So what we can show is that the probability of passing the entanglement test is very low, 1/d, which is, it's kind of like the random guessing bounds we had before for communication. Because this is true for all sigma that are separable. Okay, so that will show, but more generally, the idea of range is to consider a more general set than separable states. Why? We want to be able to potentially get a tighter bound, a tighter upper bound, and also have a measure that's computable, that can be computed easily. And so that was the idea of range. Okay, so he defined this set. Actually, it only came in follow-up work that this set was defined, but it's still attributed to range. So it's called, we call it PPT prime now. All right, it's related to PPT states. We talked about that previously, states with positive partial transpose. But it's an even further enlargement of PPT. So if you want a diagram, you can draw a diagram like this. T and then PPT prime. The PPT prime will contain operators that are not just states, but also contain substates. States with trace less than or equal to 1. So how is it defined? It's all operators that are positive semi-definite. And when you take the 1 norm of their partial transpose, that's less than 1. Okay. This itself is actually a norm, like it can be considered a partial transpose norm. And there was a recent paper in the archive that explored this and came up with measures and had this interesting conjecture. Okay. So what we're going to do, we're going to prove, first of all, maybe we should justify, I don't think we've introduced PPT prime before, right? Yeah. Why don't we justify the containment of separable in PPT prime, right? So why is sep in PPT prime? It's a strict containment. Well, if sigma is in separable states, that means you can write it as a convex combination of product states. Right? And then when you take the partial transpose, it's the same as taking the partial transpose over here. But this operator remains positive, right? A partial transpose for a separable state, in each component of the separable state, this is actually a full transpose on this state. Okay? And then a full transpose keeps a positive operator positive semi-definite, right? And then this is positive semi-definite. And so when you compute the trace norm, that's actually the same as the trace. Or if an operator is positive semi-definite, and so this will just equal 1. Right, so it's in the set. But then it contains operators beyond separable states. Right? And this set is a convex set, and you can rewrite it in such a way that it's characterized by semi-definite constraints. Okay, and so that's another use for it from a computational perspective. Okay. All right, so let's prove this for sigma in PPT prime. And it's one of those proofs, like many proofs in this course, you can stare at it for a while and wonder, well, gee, how in the world am I going to do that? And then you see a proof and it's like 2 lines. You're like, oh. So this is one of those things, all right? I don't know. Does anyone have any ideas? Has anyone looked at this before? So the first thing, let's just write down this thing that we're trying to prove. Okay. Now what? What's that?
You guys expand out the base and the maximum mistake.
Yeah, it might get you there. There's a faster way. So, all right. So we need to somehow introduce the partial transpose. Okay? So let's just apply it twice on sigma b, because the partial transpose applied twice is just the identity. All right. Let's do that. Okay. Any ideas now? What do we know about adjoint of partial transpose? Yeah, adjoint of the partial transpose is the partial transpose. So that's something you can prove. I don't know if we talked about it before, but it's something you can prove. Okay, so then that's a key step. And then once you do this, something very interesting happens. Then it's like you're almost done, actually. Okay. What is the partial transpose applied to the maximum entangled state? Why don't we actually write up this calculation? Because I think it's worthwhile. We'll do it right here. So and we're just taking the partial transpose on the same basis as phi AB, but it still works. The proof still works otherwise. Okay, so phi AB, 1 over D. Here's the 1 over D that will emerge. Okay. So that's partial this is phi AB, and then now partial transpose of it. So if we do partial transpose, then we get J, and then J and I flip, right? What is this operator? That's a swap operator. That's a unitary. Right? So this is equal to 1 over D. We'll call this just F, FAB. F for flip, swap. So that's unitary. So now we get 1 over D trace FAB DB. Now what? We have a unitary here. Well, I don't know if that's going to get it. Okay. Basically, the next thing we want to do.
The trace of the fixed state is less than this one.
Right.
Unit on a mixed state is also a mixed state. So
Yeah, but like it's not F and F dagger. Right? It is Hermitian. So we just need to remember one of those math facts. Right? Like, basically, we are at the last step now. But we haven't yet used this. Right? So like I'll just write it and then someone, if you remember, tell me why this is true. I think you might have had this in a homework problem.
Yeah, I'm trying to remember. I think it's the one I didn't write.
Oh, okay. But I think, oh, right.
It's a definition.
Yeah, it's one of those math facts, right? Like variational characterization of trace norm. So like trace norm is equal to the supremum over all unitaries. Trace UI. Remember that? Oh.
It's not just a use. So it must be less than.
Yeah, F is a unitary. That's the interesting thing that happens. So like you start with this expression, then you're trying to bound, and then you do this trick, and then, whoa, you get from phi to a unitary. Right? That's interesting. But that, let me use a fair amount in entanglement calculations. Okay, and then that's it, right? My hypothesis, sigma B is in the range set, and so this is less than 1. Less than 1. So what is the whole thing saying? It's saying, if you do the entanglement test, it gets harder and harder to pass as the dimension increases, right? And so if we're interested in, if the maximum entanglement state we're trying to make is n qubits, like n e bits, right? Then d is 2 to the n. And so that probability of passing this test is decreasing exponentially with the number of qubits, so quite rapidly. So that's the sense in which it's useless for the test. Okay. So the way you can interpret this is like, we're interested in bounding the entanglement that you can extract with the state rho, right? But now if we substitute with rho a separable state, and then we do LOCC, we remain a separable state, and the probability of passing the entanglement test is very small. Okay? What we're going to do furthermore is place here, it's unphysical because, that's the first time I did that whole semester. Got a little excited. We're going to be placing here a PBT operator. You can show that this actually implies that the trace of this is less than 1. Why is that? Let's do that. So trace doesn't change under a partial transpose. Right? And then again, use the variational characterization because it's like we implicitly have identity. Right? So then all these operators in this set are, sometimes you call it a substate because its trace is less than 1. Okay, so all these operators in here are substates. So going back to this, what we're going to be doing for the upper bound is, for n upper bound, is replace rho with sigma in this range set, and then you can show that under LOCC, you go to another operator in the range set, and then we'll use this entanglement test to see that there's like a big difference between the actual protocol, how well you could pass the entanglement test. By hypothesis, it's, the failure is less than epsilon means the success probability is greater than 1 minus epsilon. So that's quite high, if epsilon is small, is where compared to this, it's very low. And then you actually extract this parameter that's related to rate. Okay. That's how the upper bound will go, and let's do it. Any questions about it? All right, so we're going to use Rains's idea. And we're going to again use hypothesis testing relative entropy. Right? In the paper that you're reading, Connor, they're probably using hypothesis testing relative entropy, are they? Yeah. Okay. So, all right, so it's defined for state rho, and what you do is you take, similar to the other things we've seen, these kinds of entanglement measures. You take the actual state, compare it in hypothesis testing relative entropy to one that's useless for the test. That's the quantity. Okay. And what we're going to show is that distillable entanglement is less than the Rains, the epsilon Rains relative entropy. Okay. What is the proof? So we're going to consider an arbitrary protocol of this form, right? And we'll let sigma be some state, be some operator in PBT prime. Okay? Then what you can show, and I think I'm going to skip for today, is that if this LOCC channel acts on this operator PBT prime, then it preserves PBT prime. The state is the resulting operators in the set PBT prime, but for A hat B. I guess we could put this. So that you can show. We already talked about that for separable states, right? Like, if you start with a separable state and act with LOCC, it remains a separable state. Right? That's something we already talked about. And so maybe that's some intuition for why this would be true. Yeah, we'll just leave it at that. But given that, what does it imply? You can take rho and sigma and then use data processing for hypothesis testing relative entropy. Remember, we're in a converse proof now. We're in an optimality proof. And so the key concept is always going to be data processing in some way, right? So we use that now. L on rho, I'll omit the system labels, L on sigma. Okay, and then now this is in PBT prime, so taking infimum over all of them, one smaller. But this is the Rains quantity. Okay. And then, so we proved this inequality, and we proved like sigma was arbitrary, right? We chose sigma to be arbitrary. So then, that means that we can take an infimum over all sigma in the set PBT prime, and then we'll get that the Rains quantity is larger than the Rains quantity for the final state. Okay. So that's a key step. And here we're using a different notation. We can also write this like this. It's another way to write it. Some people prefer that. Okay. So now we need to use this fact. Okay, so my hypothesis is larger than 1 minus epsilon. Okay. So does anybody have an idea of what we should do? The final step. So our final step is we want to say that this is greater than log d. So how are we going to do that? Let's recall the definition of hypothesis testing relative. All right. Well, PBT prime is now playing the role of the replacer channel, right? So actually using this and this and this definition is sufficient to get this inequality. That's exactly it. Yeah, that's how it's been, with many of the things in this course. Like there's an optimization and you make a particular choice, right? So this involves an optimization over all lambda, right? So if we choose lambda, so because of the minus sign, we can exchange and make this supreme. Right? So if we plug in for omega, follow rho, and we plug in for tau, sigma, then a particular choice of lambda could be phi. The entanglement test, right? That's how you should always think of this operator. It's a measurement operator. It's like a test that you do in the states, right? And that corresponds to hypothesis testing, right? So it's like a test that you're doing in the state, and then a particular choice of the test is the entanglement test, which has outcomes 5D or identity minus 5D. And so you see here that, it's an operator, it's a measurement operator that satisfies this condition. Be larger than 1 minus epsilon for the actual state. So then L rho can go here, right? And then this will get us negative log trace phi d. We should put the hats on. Okay, sorry. We should put hats on all of these now. Right. And then sigma hat. And now what? I think you see it, right? Like this quantity is an upper bound of 1 over d, and then with negative log, it becomes log d. Now, furthermore, this inequality is holding for all choices in the set. Right? And so that means we can make this as tight as possible and take an infimum over sigma A hat B hat into the T prime. What is that? That's the range one. Right? L. Okay. So now we can eliminate the question mark. Right? Now what do we have? We have for an arbitrary entanglement distillation protocol that has error epsilon such that the final state, these dimensions are D, this bound holds, right? So it's like, if you're trying to do entanglement distillation to get epsilon approximate log base 2 of D, epsilon approximate E bits, right? Then this bound holds. Okay. So since it holds for an arbitrary entanglement distillation protocol, we can now take a supremum over all such protocols, and then that gets us the definition of distillable entanglement. That's the bound. All right. So the reasoning at a high level is very similar to what we did for entanglement assisted communication and classical communication. Right? What was the reasoning? You have the definition, which is like optimize some number of bits or whatever, subject to an error constraint. Okay. Then you look at the actual protocol versus one that's useless for the task, right? You compare them in relative entropy, use data processing, and then you need some bounds that relates how some tests, the test that judges the performance of the protocol on the useless resource, on the useless state of it, right? So for communication, it was like we had this no signaling band, with this no signaling equality. If you had to replace your channel there, your probability of passing the comparative test was 1 over the number of messages, which is no better than random guessing, right? And that's very similar here. And then data processing, da, da, da. Here, there was no, the resource that we started off with is not a channel. So there's no optimization over encodings or anything like that. We just eventually have a bound that's phrased in terms of the initial resource and the parameters for the text. Okay. So that's this bound. Very nice bound. Subsequently improved around 2018, but we won't talk about that. Okay, and furthermore, previously we said that this set has a semi-definite characterization, and because the hypothesis testing relative entropy had by inspection is a semi-definite program, that means that this quantity can be computed by a semi-definite program. Okay, and so that can be useful, mostly if the dimension of the state is small. Right? Otherwise, it's going to be difficult for classical algorithm. But maybe with quantum algorithms, it would be better. Okay. Good. All right, then we can do other kinds of things that we've done before. Other kinds of bounds we can get are similar to what we've seen before. Or tilde alpha. This will hold for all alpha greater than 1 and epsilon between 0 and 1. How do we get this? This kind of thing we've probably done like 4 times now, right?
So instead of
Yeah, that's right, sandwiched. Do you remember the inequality? So this thing, right? I won't write the state. This kind of thing we've used a lot. Right? Hypothesis testing relative entropy is less than sandwich plus the correction. And this can be used to show that the range relative entropy. So this I won't show in detail because we talked about that. But there's the asymptotic distillable entanglement. And this you define as a limit. We take same kind of thing. Space here. You evaluate for a tensor power state. So rather than a single state, we allow for tensor products. That's meant to be like you're generating the state over time, right? It's coming from some source over time. And it's generated this IID way. So we can use this bound to get the distillable entanglement is less than the range relative entropy. Or you get this quantity by replacing in the definition dH epsilon with the usual quantum relative entropy. Okay. And so this is the bound that Raines got back in the late 90s. Yes, and we can even use this to get a strong converse where we flip in the definition M's to soups. Okay, similar to what we've done before. Okay. I want to at least mention squashed entanglement since we talked about that before. And a bound that you can get for the one-shot scenario. So you can get this bound. I say similar ideas, but I mean from like a broad perspective. Okay, so this G function is x plus 1 log base 2 x plus 1 minus x log x. So that bound you can get. How do you get it? Here, actually, this proof right here is essentially saying that this range quantity is an entanglement monotone. Why? We used it to prove that if you apply an LOCC channel, then the quantity does not increase. That's the definition of entanglement measure. Right? So we know that squash entanglement is an entanglement measure. Right? So we could say, as a first step, squash entanglement of rho is greater than squash entanglement of L of rho. Okay. And then the next step is something that is more complicated, but there's a continuity. There's a continuity inequality for squash entanglement. It allows you to say, like, if we know that fidelity between tau and omega is greater than 1 minus epsilon, then you can say the squash entanglement, the difference between the squash entanglement of tau and the squash entanglement of omega is less than some epsilon prime. Okay, so you use that, and the epsilon prime is related to what's appearing in front here. Okay, it's G2, and the target state. So this is a fidelity between maximum entangled state and the target state, and it's larger than 1 by subset. So we can plug into this continuity inequality, and omega is like the final state of the protocol, tau is like the maximum entangled state. And if you evaluate the squash entanglement of the maximum entangled state, it's log D. It's log D. So that's how this kind of thing arises with squash entanglement. So you get like, log D minus some correction term that comes out of it. Okay. But there's quite a bit of technical detail that goes into this kind of statement. All right. I just wanted to show you that because the range quantity, at least for asymptotic distillable entanglement, the best known bounds that have not changed since about 2005 are the range quantity and the squash entanglement. So, it would be a breakthrough result for entanglement theory to get a better balance. Right? I should also add that you can regularize the range quantity. So you can do this kind of thing, or reg. Limit as n goes to infinity. The n range. You evaluate for the tensor power state. So if you evaluate the range quantity for the tensor power state, take the limit, and then you can actually show that that's an upper bound still. And so this, it gets better. That's the thing. So when we talked about communication, it's a good point you're raising. When we regularize, the quantity got larger. Here, when you regularize, it gets smaller. Why is that? It has to do with the definition of the range quantity. That's right. That's exactly right. Yeah. So the range quantity is like this. Let's look at like a two-party thing. Right? A1, A2, A1, A2. And plug in tensor power states. Right? So you plug that in, but now we take a themum over operators in this thing, A1, A2. B row 1, B1, tensor row, B2, 2 sigma. Okay. So you can make a choice of a tensor product, sigma A1, B1, tensor sigma A2, B2, and then use additivity to show that the range quantity will be subadditive. Right, and then that, but it's not known to be additive. And I think there are explicit examples where it's not additive. So it actually gets smaller as you increase n, and so that's why it gets to be a better. But then it becomes uncomputable if you do this regularization. But you could look at like finite n and say like, oh, I'll take n2 or 3, and that's what I'm willing to tolerate. So those are the best upper bounds known. Yeah. It's been like that for a while. All right. Any questions on this stuff? Squash entanglement is additive. So this regularization doesn't do anything for it. It's already additive. The main problem with squash entanglement is you have this infimum over an extension system that can be arbitrarily large. And so that's what makes it hard, if not impossible, to compute. But then if you're interested in an upper bound, you just try to make clever choices of the extension. You get an upper bound. All right. If there are no other questions about the upper bound, we'll move on to lower bounds. Okay. So here for the lower bound, I'm really just going to give you a taste of the main idea. And the main concept is something called decoupling. Okay, and just as we chose, remember when we had codes for communication, at least unassisted communication, we chose random codes. Okay? Turns out that idea is very effective for entanglement distillation and quantum communication. But there's a different way that you choose a random code. It's just like you choose a random unitary. Okay, so lower bound still entanglement. Okay. I just want to first make some comments about the lower bounds on asymptotic distillable entanglement. So asymptotic quantity we just defined, right? And what you can show is that this is bounded from below by the coherent information. That was a quantity we learned about before. And it's the difference of the marginal bond donor entropy for Bob and the joint entropy. Okay. And there is a directionality. So with the coherent information, you see the notation. There's a directionality. It's like A to B, right? This lower bound uses one-way LOCC from Alice to Bob. Just one round, okay? So that happens, and we'll see it in the proof we construct. That'll be the form. Is where in general entanglement distillation, you allow for arbitrary LOCC back and forth. So, you know, there can be improvements over this. There's no reason for the communication to be just from Alice to Bob in this one-way LOCC. It could also be from Bob to Alice. If you do that, then you also get, if you reverse things, then you get this. Just the role of Alice and Bob flips. And this means the communication goes from Bob to Alice. And that could potentially have a higher rate in some scenarios, and so you'd want to do that. In the context of quantum key distribution, this is called reverse reconciliation. Okay, just some terminology. All right, so that's what you get in the asymptotic case. Let's now try to justify it, and I will do my best in the remaining time. So for this, we need to define some other quantities. I believe we've talked about max relative entropy. So defined like this. The smallest value of lambda such that this operator inequality can hold. And then from this, you can define conditional min entropy. of a bipartite state. And that's meant to be another kind of variant of conditional entropy. Right? So here you put a minus sign in front and themum over state sigma b, and the max relative entropy between rho AB and this one. Okay. You can kind of think of it up to a scalar as comparing your state to a product state where the first one's maximum mixed. You can kind of think of it that way. But to think of it that way, you'd have to put like a minus log. I forget which way it is, but it might be a minus log or a plus log, the dimension of the system. Okay. Right, and then we do this. We'll define, it's called a ball of nearby states, epsilon ball. So rho tilde is a state. And then here we'll use what's called sign distance. Because this is somehow like a, if these were pure states, this quantity would be the sine of the angle between those pure states, right? Okay. And then once we have that, we can define smooth conditional min entropy. It's like this. You just take the unsmoothed one and you smooth it. So you just optimize over nearby states in the ball, and then calculate the min entropy of the nearby state. And the idea behind this is like this. So what we're going to show is that this quantity is going to be like the number of EBITs that you can extract from rho AB. The number of exact EBITs without error at all. Okay, so that's how you should think about it roughly. But we always allow for a little error, right? And so this is saying, oh, well, you know, if we use a nearby state, no one's going to notice up to like an epsilon error probability. So we might as well do that. And we might get many more EBITs out, right? And so you use this one.
It's like a proximal operator.
Yeah. And we've been doing research with quantum semi-different programs and optimization of this notion. Yeah. Okay. Good. So what is the theorem that we want to try to justify? So for a state rho AB, epsilon between 0 and 1. Now we have this eta quantity, eta variable again between 0 and epsilon. Actually, all right. We can show that the distillable entanglement of rho is greater than this smooth min entropy E. Psi ABE purifies rho. So my explanation before was a little off in terms of connecting this to this. just in the previous explanation, replace this quantity with A given E in the purification of rho AB, right? And then the arguments I was saying was smoothing that applies. Right? So, but, you know, this is the statement we can make. Okay. All right. So in the remaining time, we'll try to just go through the basic idea of the proof, but keep in mind there are many calculations we're just going to omit. Okay. So what is the basic idea of the proof? Apply a random unitary so this is the first thing Alice will do. So just hit her system with a random unitary, okay? And what we're going to do is, like with Shannon's argument, you know, it might seem like stupid to pick a code randomly, but why would that work, right? But then the argument is a probabilistic method to say, oh, you know, there exists at least one that'll do the job, right? That'll do a good job. And usually it's in like an asymptotic limit. But you know, here we're considering the one-shot case. So this random unitary is like a random code. You know, it's like a random rotation of your space. Okay. That's the first thing. And then what we're going to argue is that there exists a choice that will do very well for entanglement distillation. So when you do this, you'll get that state. Now what? Now Alice will apply a measurement. The measurement will have a simple form. Right? So the measurement will be a, we always think of things as channels, so it'll be a quantum to classical and quantum channel. Right? So the input will be quantum, the outputs will be quantum and classical. All right, so that channel will be right as E because it'll be kind of like an encoder. So it will just be her Hilbert space is dimension. Think of it like this. This will be Alice's Hilbert space. And we'll suppose for simplicity that you know, the dimension of A divided by the dimension of the target system is an integer. We'll just make that assumption for simplicity. Okay. And we'll just divide up the space into, this is meant to be even subspaces, right? So like, you know, if dA were 20, you know, this would be spanned by basis states 1, 2, 3, 4, 5, basis states 6, 7, 8, 9, 10, etc. So it's just, you know, divided up, and so there'll be a projector here, pi1a, pi2a. So that would be the projection onto 1, 2, 3, 4, 5, 5. Okay, and so that's the measurement that will be done. And then, depending on the outcome, there'll be a target space where Alice will just apply an isometry to get to that target space. And so like, if the target space is 1, 2, 3, 4, 5, then this mapping here will just be the identity. This mapping will map 6, 7, 8, 9, 10 to 1, 2, 3, 4, 5, right? And so that's what it does. That's the channel. So it's pretty simple. These will be these maps, 1, 2, 3, 4. And the outcome will be stored, measurement outcome will be stored in a classical register XA. That will be forwarded to Bob. That'll be the classical outcome of the measurement, the classical communication forwarded to Bob. So LOCC consists of unitary, this measurement, which is kind of like divides up the space, right? And he reorganizes it here. Send the classical outcome to Bob, and then we'll describe later what Bob does. Okay. So the key thing that can be shown through a lot of steps is a decoupling. It's called a decoupling lemma. Okay, and so the idea is that the final space A hat. That's the dimension of the final space where the approximate maximum entangled state will go. So if that is this size, the log of the dimension is this size, then you have a decoupling state. Okay, that's the argument. So there exists a choice of unitary, UN, such that Px will be the probability that you get outcome X when you perform it, when you do all this stuff in the actual state of the protocol. And this is dimension of the classical system. Here's a fidelity. So the argument will be that the fidelity between the actual state of A hat and the environment system is close in fidelity to a decoupled state, a product state. That's the statement. So let me explain this a bit and just give you some basic sense. If we have a bipartite state, rho AE, and say that A is a qubit and E is a qubit, okay? And we do a random Pauli operator. Right? If we send this through apply a random Pauli operator, then what happens? This amounts to a trace of system A and replaced by a maximum mixed state, tensored with the marginal on system A. Okay? And so when you do this random unitary, you decouple. Okay, so that's kind of like a very brutal random unitary. And what you're doing here is pretty analogous. Okay. So, but the statement, here we have an exact equality, right? But here we have like some wiggle room with epsilon. Okay. And then for this to happen, it was like we needed the dimension of the target system to be this, the log of it to be this large to get a good decoupling. Okay, why is this useful? This may seem like, well, what in the world did we accomplish by doing this, right? But this actually gives us an exit to entanglement distillation. Why? These states here don't feature Bob systems, right? Let's write down the definition of omega x. First of all, P of x is the probability that you get outcome x when doing this measurement on system A after doing the random unitary. Okay. And omega x is the post-measurement state. So we do this channel on the pure state. Oh, I forgot to do the unitary. And then the isometry, the x goes to normalized by. That's the state of the actual protocol. So the point is, there exists a unitary such that this condition is true. So, what can we do now to incorporate? Wow. Well, you see that this state right here, this is actually a pure state. If you have a pure state, you do a unitary, that's still a pure state. If you project a pure state on one system and normalize it, it's still a pure state. So this is a pure state, and then isometry doesn't affect the purity as well. So this is a pure state. Trace over Bob, and then we get omega. The point is, before the trace, this is a pure state. So this right here purifies omega x, the actual state. Okay. I suppose we should call this whole thing psi x a hat b e. Okay, it's a pure state, and it purifies omega x a hat e. All right. We can make a choice of a purification of this state, right? What purifies maximum mixed state? Well, maximum entangled, right? So if we choose this to be the b hat here, then we can also purify this state by, we'll call it phi e b prime, or we do it this way. This, if we trace over b hat and b prime, gives back this state. So now, what do we do next? We're talking about fidelity, mixed states, we're constructing purifications. What's the next natural theorem we should apply?
They're related by isometries.
Yeah, exactly. Ullmann's theorem, right? So Ullmann's theorem there exists an isometric channel W depends on X going from this system B to B hat and B prime, such that this fidelity of omega X And now we have the fidelities, but with the isometry relating the purifications. So fidelity psi x A hat B E. Phi A B hat. Okay, so that means in this expression, we can substitute this, right? So that's the end of the proof, right? Why is it the end of the proof? Well, this, what we get from Ullmann's theorem is acting on Bob systems. The thing was, these states were those of, these systems belong to Alice and the environment. And then who purifies that is Bob. Right, so this, what Ullmann's gives us is the decoder of Bob to decode the entanglement, right? It's like, oh, if this decoupling condition is satisfied, which is some mathematical statement you have to prove using random unitaries, then you're kind of free from there because it says, well, Bob can apply this channel to the states resulting from Alice's systems. He needs to know the value of X through the classical communication, he knows it, to apply the correct isometry. And then at the end, his state will be a tensor product of the desired state here and something else. And then he can just discard that part. He can throw away system B prime. So that's the full proof. We're right on time. Well, that's the idea of the proof, okay?
I feel very similar to the state merging idea.
Yeah, yeah.
It has a
We get state merging.
reality, the condition of the maximum mixed state and the environment.
Oh, we also get state merging from this. We didn't do it in the book, but this right here is close to, so, okay, sorry, talking about state merging. We haven't talked about that. So let's finish off the proof. Let's just make a summary statement and then we'll return to the statement about state merging. Okay, so what are the steps? One, Alice applies UA. It has to be the UA guaranteed by this theorem. This was the whole thing, right? And then this has a lot of a very detailed and technical mathematical proof to get to this point. Right? So Alice applies UA, then this encoding channel, which is just like a simple thing divided up the space. Right? Okay. Alice sends the classical system XA to Bob. Right? What does that do? That tells him the value in here. Right? And then once you have that, Bob applies a decoding channel. We'll just call it trace B prime X. Based on X, which is the value in this register. And then once he does that, you can substitute in this expression here, this fidelity, right? And then it's saying like, you could do more tricks to just get it to say that the final state of the protocol is close to phi with fidelity greater than 1 minus epsilon. That's the final state. Okay. And so that's kind of it. but, what were the main ideas? It kind of totally, it's not clear why the conditional min entropy is there, but that's there because it's what's needed to get the decoupling. You should think of it roughly like that. So the main concepts were random coding, but in a totally different way, with the random unitary. Then this decoupling statement, which we can, we know Ullmann's theorem very well. We've used that a number of times. And so once we have this, it's just using Ullmann's theorem and then thinking about an LOCC to do the predict. Okay. So that's the full statement. Let me talk a bit why this is, how is this related to coherent information? Okay. Because that was a statement we made earlier. So how is this related to coherent information? So if you think the limit is n goes to infinity, 1 over n h min smooth. This evaluated for n copies of the pure state. I don't think you need the epsilon limit on 0. You can prove that this goes to conditional entropy. Okay. How is this related to coherent information? This, we use things that we learned about in the entropy lecture. Right? So psi ABE is a pure state. This you can write as, by definition, this entropy difference. And now we use the fact that this entropy is equal to the entropy of B. Right? If you're a pure state, you make a bipartite cut. So if you make the cut between A, E, and B, then you get this psi minus H of E, bipartite cut A, B. And then that's coherent information. So that's roughly why you get coherent information in the asymptotic limit. Okay. Good. Let's address the point that Soria was making. What is state merging? So state merging is a protocol that Soria was studying within the summer. Yeah. It's been around since 2005. And the idea is this. There's a state, OAB, and it's purified by the system E. Right? That's what we're doing throughout. Then you allow for LOCC, and not only do you try to distill entanglement, but you want at the end for there's an original state here, and you want it such that Alice's system gets transferred to Bob. So it's called this A tilde BE. And so then the term merged is used because, like, in this process, not only are they distilling entanglement, but also Alice's share of the state gets sent over to Bob. You could also call it state transfer, which I think is a better name. So that can be accomplished also. How do we see that here? So I believe we can see it from this, and there's an assumption that, rho tilde, we didn't state it, but there's an assumption that this kind of thing holds. It might be epsilon or something different. Where rho E is the marginal of this state. Well, this is purified by psi ABE, right? And so that's the idea. Rather than thinking of this as just something that purifies E, we can actually make the choice here for this to be psi A tilde BE, right? And so this decoder could go from B to B hat and A tilde B. And then it would accomplish the state merging. So rather than throwing this part away, rather than you would actually keep it. And you would get the entanglement and transfer Alice's share of the state. So you'd accomplish the state merging task. The whole discussion, we were assuming the coherent information is non-negative. And that was an assumption. But it may not be the case, in which case this whole proof doesn't even make sense in that scenario. But I think the main thing that happens is you will no longer be able to extract entanglement, but you actually have to invest entanglement to accomplish the state merging task. So anyway, but the whole time we were assuming that this was non-negative, so that you could actually do entanglement distillation. All right, so that's all. Unless there are any questions about what we talked about. All right, I enjoyed teaching you all this semester. I had fun. It's very nice to have this small environment with graduate students. Very different from teaching engineering undergrads. Maybe you know how that is since you've been TAs yourself. So anyway, it will be your turn on Wednesday. And I'll send a Zoom link very soon.
So Wednesday also on Zoom? Or
Wednesday and Friday on Zoom.
Okay.
Yeah.